Hello, it's Stat 134, Lecture 24. Last time we did the change of variable formula for densities. So here is a picture of a many to one or a 3 to 1 function. And the change of variable formula has the following idea. Basically, y to be in dy is equivalent to x being in one of the three dx's shown in the picture here. And these dx's are all disjoint from one another, so by the addition rule, the probability that y is in dy is a sum of the probability that x is in dx for each of these dx's. So now, dividing through by dy's here, we get the change of variable formula, except that we have dx over dy, but dx over dy is the same as 1 over dy over dx here, as long as dy over dx is not 0. So that's the inverse function theorem in calculus, actually. So in fact, we have 1 over g prime of x. And the reason for the absolute value is just because we can't have the dx be negative, because all these probabilities are positive quantities. So now, so actually this is quite straightforward, and then there's one more step, and you just need to plug in x as a function of y into your formula here. So x is one of the g inverse y values, and you need to plug that in for each of these formulas. So today we're going to do, first we're going to go over some of your explanations from the concept test, and this is to provide you with some different points of view on how to solve that problem we did last time. And the cumulative density function, the CDF, we're going to discuss from section 4.5, its main use being to describe a distribution. So remember last time our concept test for let v be a standard normal random variable, the distribution of x equal v squared is. So it turns out to be a gamma, and the reason is that, so here we have a 2 to 1 function, and the numerator f of x, or in this case f of v, so f of v has a v squared in it, and so it takes the same value whether v is plus or minus square root of x. So and then the bottom has an absolute value sign, so that's also the same when you plug in plus or minus square root of x. So actually we have two of the same terms that we add together, so hence the 2 in the front. And then we can see that this is a gamma with r as 1/2 and lambda is 1/2. So one student writes correctly, this is a change of variable from v equals norm 0, 1 to x is v squared. Plugging in, you see that the variable part consists of e to the minus x over 2 over the square root of x. This matches gamma. Perfect. Some incorrect responses, you get standard normal divided by v. So the reason this student is thinking that is the student has forgotten to plug in v equals plus or minus square root of x. And so it looks like they're getting standard normal divided by v. Another student writes it's like a gamma distribution and a Gaussian distribution mixed. Again, same problem. And another student writes, if we have a normal distribution and square a random variable, then we'll see that it stays normal. Incorrect. Then we move to section 4.5, the cumulative distribution function. Remember that x being a random variable, the CDF is the probability that x is less than x. So, for example, for Bernoulli, on the left I have the probability mass function. In parentheses, I have the probability for each of those masses. And on the right, I have the CDF. For the uniform, again, the height for the non-zero part is 1 over b minus a. The antiderivative of that is 1 over b minus a times x, and hence the CDF has a slope, is linear with a slope 1 over b minus a. For exponential, f of t follows the exponential formula, lambda e to the minus lambda t, the density, and the CDF is 1 minus the survival function, so it's 1 minus e to the minus lambda t, which has the graph shown. So an interesting example is a mixed distribution, which is part continuous, part discrete. So let t be exponential lambda, c be a positive constant, and x be t if x is less than c, and c if x is c. So for x less than c, this just follows a t distribution. So I've written the density for t. So what I've shown in green here is like if I were to continue just the density for exponential, but t is killed by c, which means that at c, whatever leftover probability there is, which in this case turns out to be e to the minus lambda c, all goes into a mass function. So this is part continuous, part discrete, and the CDF now has a jump in it. So the CDF is the same CDF that you get for t up to c, but after c there's a jump, and the gap here is exactly e to the minus lambda c. Then I asked you guys to find the CDF of t, which has the density 1/2 lambda e to the minus lambda absolute value t. This is called a double exponential. Its graph is basically two-sided exponential, and you should be able to draw the rough shape of it. Then finding actually what these parts are, you could do this with calculus, for example. Just take a look what I've done here. And one student asked about there being a kink in it, and so I show that the slope of the CDF is lambda over 2 from the left, and it's lambda over 2 from the right, so there is no kink. Then we did a concept test. Suppose you're trying to discretely leave a party. Your time to leave is uniform from 0 to 2 minutes. However, if your walk to the exit takes more than 1 minute, you run into a friend at the door and must spend the full 2 minutes to leave. Let t represent the time it takes you to leave. True or false, the graph of the CDF of t is this picture shown on the right here. So that would be incorrect. It's not incorrect because it looks like it's starting at 1/2. Instead, this picture is 0 up to 0, and then there's a jump to 1/2. But it's just actually not the CDF of what's being described here. What is being described here? Let's take a look at what the density is. So the density is that, well, we would have a uniform from 0 to 2 with height 1/2, but that uniform gets killed by well, killed, I don't know if it's the right term, but basically once you're walking for more than 1 minute towards the exit, you're stopped at the door, and so it takes you a full 2 minutes to leave. So the values that t takes is between 0 and 1 and 2. There's no other non-zero value that it takes. There's no other value that it takes, right? So now the chance of being between 0 and 1 is 1/2, and so the remaining probability namely that the time is 2, is also 1/2. So you can make this into a CDF. So essentially, so it's linear up to 1/2, and then it stays the same height as you're talking, and then there's a jump at 2. Then there was a follow-up question. Suppose stoplights at an intersection alternately show green for 1 minute, red for 1 minute. There's no yellow. Suppose a car arrives at the light at a time distributed uniformly from 0 to 2 minutes. Let x be the delay of the car at the lights. True or false, the graph of the CDF of x is what's shown here. So it's actually true. You can take a look at what the density is. So the density here, the density is, so this is the density for the delay, right? So the delay, so what are the possible values of the delay? You could have no delay, or the most delay that you could have is 1 minute, right? So when do you have no delay? You have no delay when you arrive at a green light. What's the chance of you arriving at a green light? Well, the car's arrival at the light is distributed uniformly from 0 to 2 minutes. So roughly there's a chance of 1/2 that you're going to arrive during a green light. So the probability that your delay is 0 is 1/2, and then the delay the delay is uniform between 0 and 1, because your time of arrival at the red light is uniform, right? You arrive randomly at any time between 0 and you arrive randomly at any time in that 1 minute that you have the red light. So the delay is uniformly anything between 0 and 1, but we've already used 1/2 of our probability for the mass at 0, leaving 1/2 probability left. And so the CDF is we're 0 until till x is 0. Then there's a jump to 1/2, meaning that we're at the green light for probability 1/2, and then we have the red light uniform after that. So that is the show, and I will see you next time.